three-dimensional geometry. Introduction. In this chapter, we shall study the direction cosines and direction ratios of a line joining two points and also discuss about the equations of lines and planes in space under different conditions, angle between two lines, two planes, a line and a plane, shortest distance between two skew lines and distance of a point from a plane. Most of the above results are obtained in the vector form. Direction cosines and direction ratios of a line.
If a directed line L passing through the origin makes angles alpha, beta and gamma with x, y and z axis respectively called direction angles, then cosine of these angles, namely cos alpha, cos beta and cos gamma, are called direction cosines of the directed line L. If we reverse the direction of L, then the direction angles are replaced by their supplements, that is pi minus alpha, pi minus beta and pi minus gamma. Thus, the signs of the direction cosines are reversed. Note that a given line in space can be extended in two opposite directions, and so it has two sets of direction cosines. In order to have a unique set of direction cosines for a given line in space, we must take the given line as a directed line. These unique direction cosines are denoted by L, M and N.
Direction cosines and direction ratios of line. If the given line in space does not pass through the origin, then in order to find its direction cosines, we draw a line through the origin and parallel to the given line. Now, take one of the directed lines from the origin and find its direction cosines as two parallel lines have same set of direction cosines. Any three numbers which are proportional to the direction cosines of a line are called the direction ratios of the line. If L, M, N are direction cosines and A, B, C are direction ratios of a line, then A equal to lambda L, B equal to lambda M and C equal to lambda N. For any non-zero, lambda I cap R.
Relation between the direction cosines of a line. Consider a line RS with direction cosines L, M and N. Through the origin, draw a line parallel to the given line and take a point P, X, Y, Z on this line. From P, draw a perpendicular PA on the x-axis. Let OP is equal to R. Then cos alpha is equal to OA by OP is equal to X by R. This gives X is equal to L into R. Similarly, Y is equal to MR and Z is equal to NR. Thus, X square plus Y square plus Z square is equal to R square into L square plus M square plus N square. But X square plus Y square plus Z square is equal to R square. Hence, L square plus M square plus N square is equal to 1. Direction cosines of a line passing through two points. Since one and only one line passes through two given points, we can determine the direction cosines of a line passing through the given points P, x1, y1, z1 and q, x2, y2, z2 as follows. Let L, M and N be the direction cosines of the line PQ and let it makes angles alpha, beta and gamma with the x, y and z axis respectively. Draw perpendiculars from P and Q to xy plane to meet at R and S. Draw a perpendicular from P to QS to meet at N. Now, in right angle triangle PNQ, angle PQN is equal to gamma. Therefore, cos gamma is equal to NQ by PQ is equal to Z2 minus Z1 by PQ. Similarly, cos alpha is equal to X2 minus X1 by PQ and cos beta is equal to Y2 minus Y1 by PQ. Hence, the direction cosines of the line segment joining the points P, X1, Y1, Z1 and Q, X2, Y2, Z2 are X2 minus X1 by PQ, Y2 minus Y1 by PQ and Z2 minus Z1 by PQ, where PQ is equal to the square root of X2 minus X1 whole square plus Y2 minus Y1 whole square plus Z2 minus Z1 whole square.
Direction cosines of a line passing through 2 points. The direction ratios of a line segment joining P, X1, Y1, Z1 and Q, X2, Y2, Z2 may be taken as X2 minus X1, Y2 minus Y1, Z2 minus Z1 or X1 minus X2, Y1 minus Y2, Z1 minus Z2.
If a line makes angle 90 degree, 60 degree and 30 degree with the positive direction of X, Y and Z axis respectively, find its direction cosines. Solution. Let the direction cosines of the lines be L, M and N. Then L is equal to cos 90 degree which is equal to 0. M is equal to cos 60 degree which is equal to 1 by 2 and N is equal to cos 30 degree which is equal to root 3 by 2.
If a line has direction ratios 2, minus 1, minus 2, determine its direction cosines. Solution. Direction cosines are 2 by root 2 square plus minus 1 whole square plus minus 2 whole square, minus 1 by root 2 square plus minus 1 whole square plus minus 2 whole square, minus 2 by root 2 square plus minus 1 whole square plus minus 2 whole square, or 2 by 3 minus 1 by 3 minus 2 by 3. Example. Find the direction cosines of a line passing through 2 points minus 2, 4, minus 5 and 1, 2, 3. Solution. We know the direction cosines of a line passing through 2 points. P, X1, Y1, Z1 and Q, X2, Y2, Z2 are given by X2 minus X1 by PQ, Y2 minus Y1 by PQ, Z2 minus Z1 by PQ, where PQ equal to root X2 minus X1 the whole square plus Y2 minus Y1 the whole square plus Z2 minus Z1 the whole square. Here, P is minus 2, 4, minus 5 and Q is 1, 2, 3. So, PQ equal to root 1 minus minus 2 the whole square plus 2 minus 4 the whole square plus 3 minus minus 5 whole square equal to root 77. Thus, the direction cosines of the line joining 2 points is 3 by root 77, minus 2 by root 77, 8 by root 77. Example. Find the direction cosines of x, y and z axis. Solution. The x-axis makes angle 0 degree, 90 degree and 90 degree respectively with x, y and z axis. Therefore, the direction cosines of x-axis are cos 0 degree, cos 90 degree, cos 90 degree, that is 1, 0, 0. Similarly, direction cosines of y-axis and z-axis are 0, 1, 0 and 0, 0, 1 respectively.
Show that the points A, 2, 3, minus 4, B, 1, minus 2, 3 and C. 3, 8, minus 11 are collinear. Solution. Direction ratios of line joining A and B are 1 minus 2, minus 2 minus 3, 3 plus 4, that is minus 1, minus 5 and 7. The direction ratios of line joining B and C are 3 minus 1, 8 plus 2, minus 11 minus 3, that is 2, 10, minus 14. It is clear that the direction ratios of AB and BC are proportional. Hence, AB is parallel to BC. But point B is common to both AB and BC. Therefore, A, B and C are collinear points.
Equation of a line in space. We have studied equation of lines in 2 dimensions in the previous class. We shall now study the vector and Cartesian equations of a line in space. A line uniquely determined if 1. It passes through a given point and has a given direction, or 2. It passes through 2 given points, vector r is equal to vector a plus lambda vector b.
Equation of a line through a given point and parallel to a given vector B. Let A vector be the position vector of the given point A with respect to the origin O of the rectangular coordinate system. Let L be the line which passes through the point A and is parallel to a given vector B. Let R vector be the position vector of an arbitrary point P on the line. Then AP vector is parallel to the vector B, that is AP vector is equal to lambda B vector, where lambda is some real number. But AP vector is equal to OP vector minus OA vector, that is lambda B vector is equal to R vector minus A vector. Conversely, for each value of the parameter lambda, this equation gives the position vector of a point P on the line. Hence, the vector equation of the line is given by R vector is equal to A vector plus lambda B vector. Derivation of Cartesian form from vector form. Let the coordinates of the given point A, B, x1, y1, z1 and the direction ratios of the line B, A, B, C. Consider the coordinates of any point PB, x, y, z. Then R vector is equal to xi cap plus yj cap plus zk cap. A vector is equal to x1 cap plus y1 j cap plus z1 k cap, and B vector is equal to ai cap plus bj cap plus ck cap. Substituting these values in 1 and equating the coefficients of I, j and k, we get x is equal to x1 plus lambda a, y is equal to y1 plus lambda b, z is equal to z1 plus lambda c. These are parametric equations of the line. Eliminating the parameter lambda from 2, we get x minus x1 by a is equal to y minus y1 by b is equal to z minus z1 by c. This is the Cartesian equation of the line. Find the vector and the Cartesian equation of the line through the point 5, 2, minus 4 and which is parallel to the vector 3i cap plus 2j cap minus 8k cap. Solution. We have A vector is equal to 5i cap plus 2j cap minus 4k cap and B vector is equal to 3i cap plus 2j cap minus 8k cap. Therefore, the vector equation of the line is R vector is equal to 5i cap plus 2j cap minus 4k cap plus lambda into 3i cap plus 2j cap minus 8k cap. Now, R vector is the position vector of any point P, x, y, z on the line. Therefore, xi cap plus yj cap plus zk cap is equal to 5i cap plus 2j cap minus 4k cap plus lambda into 3i cap plus 2j cap minus 8k cap is equal to 5 plus 3 lambda into I cap plus 2 plus 2 lambda into j cap plus minus 4 minus 8 lambda into k cap. Eliminating lambda, we get x minus 5 by 3 is equal to y minus 2 by 2 is equal to z plus 4 by minus 8, which is the equation of the line in Cartesian form. Derivation of Cartesian form from vector form. We have r vector is equal to xi cap plus yj cap plus zk cap. A vector is equal to x1 cap plus y1 cap plus z1 cap and b vector is equal to x2 cap plus y2 cap plus z2 cap. Substituting these values in 1, we get xi cap plus yj cap plus zk cap is equal to x1 cap plus y1 cap plus z1 cap plus lambda into x2 minus x1 into I cap plus y2 minus y1 into j cap plus z2 minus z1 into k cap. Equating the like coefficients of I cap, j cap and k cap, we get x is equal to x1 plus lambda into x2 minus x1, y is equal to y1 plus lambda into y2 minus y1, z is equal to z1 plus lambda into z2 minus z1. On eliminating lambda, we obtain x minus x1 by x2 minus x1 is equal to y minus y1 by y2 minus y1 is equal to z minus z1 by z2 minus z1, which is the equation of the line in Cartesian form. The Cartesian equation of a line is x plus 3 by 2 is equal to y minus 5 by 4 is equal to z plus 6 by 2. Find the vector equation for the line. Solution. Comparing the given equation with the standard form, x minus x1 by a is equal to y minus y1 by b is equal to z minus z1 by c. We observe that x1 is equal to minus 3, y1 is equal to 5, z1 is equal to minus 6 and a is equal to 2, b is equal to 4, c is equal to 2. Thus, the required line passes through the point minus 3, 5, minus 6 and is parallel to the vector 2i cap plus 4j cap plus 2k cap. Let r vector be the position vector of any point on the line. Then the vector equation of the line is given by r vector is equal to minus 3i cap plus 5j cap minus 6k cap plus lambda into 2i cap plus 4j cap plus 2k cap. Angle between two lines. Let L1 and L2 be two lines passing through the origin and with direction ratios A1, B1, C1 and A2, B2, C2 respectively. Let P be a point on L1 and Q be a point on L2. Consider the directed lines OP and OQ as given in the figure. Let theta be the acute angle between OP and OQ. Now, recall that the directed line segments OP and OQ are vectors with components A1, B1, C1 and A2, B2, C2 respectively. Therefore, the angle theta between them is given by derivations.
Angle between two lines. Derivations. The angle between the lines in terms of sin theta is given by sin theta equal to root 1 minus cos square theta equal to root 1 minus a1 a2 plus b1 b2 plus c1 c2 the whole square by a1 square plus b1 square plus c1 square into a2 square plus b2 square plus c2 square equal to root a1 square plus b1 square plus c1 square into a2 square plus b2 square plus c2 square minus a1 a2 plus b1 b2 plus c1 c2 the whole square by root a1 square plus b1 square plus c1 square into root a2 square plus b2 square plus c2 square equal to root a1 b2 minus a2 b1 square plus b1 c2 minus b2 c1 whole square plus c1 a2 minus c2 a1 the whole square by root a1 square plus b1 square plus c1 square into root a2 square plus b2 square plus c2 square equation 2. Instead of direction ratios for the lines L1 and L2, direction cosines namely L1 M1 N1 for L1 and L2 M2 N2 for L2 are given. Then 1 and 2 takes the following form. Cos theta equal to mod L1 L2 plus M1 M2 plus N1 N2 ASL 1 square plus M1 square plus N1 square equal to 1 equal to L2 square plus M2 square plus N2 square equation 3 and sin theta equal to L1 M2 minus L2 M1 whole square minus M1 N2 minus M2 N1 whole square plus N1 L2 minus N2 L1 whole square equation 4. Two lines with the direction ratios A1 B1 C1 and A2 B2 C2 are first perpendicular, that is if theta equal to 90 degree by equation 1 A1 A2 plus B1 B2 plus C1 C2 equal to 0. 2. Parallel, that is if theta equal to 0 by equation 2 A1 by A2 equal to B1 by B2 equal to C1 by C2. Now, we find the angle between two lines when their equations are given. If theta is acute, the angle between the lines R vector equal to A1 vector plus lambda B1 plus R vector equal to A2 vector plus mu B2 vector. Then, cos theta equal to mod B1 vector into B2 vector by mod B1 vector mod B2 vector. In Cartesian form, if theta is the angle between the lines, x minus x1 by a1 equal to y minus y1 by b1 equal to z minus z1 by c1 equation 1 and x minus x2 by a2 equal to y minus y2 by b2 equal to z minus z2 by c2 equation 2 where a1 b1 c1 and a2 b2 c2 are the direction ratios of the line 1 and 2 respectively. Then cos theta equal to mod a1 a2 plus b1 b2 plus c1 c2 by root a1 square plus b1 square plus c1 square root a2 square plus b2 square plus c2 square.
Find the angle between the pair of lines given by r vector is equal to 3i cap plus 2j cap minus 4k cap plus lambda into I cap plus 2j cap plus 2k cap and r vector is equal to 5i cap minus 2j cap plus mu into 3i cap plus 2j cap plus 6k cap. Solution. Here, B1 vector is equal to I cap plus 2j cap plus 2k cap and B2 vector is equal to 3I cap plus 2j cap plus 6k cap. The angle theta between the two lines is given by cos theta is equal to modulus of B1 vector dot B2 vector by modulus of B1 vector into modulus of B2 vector. Substituting the values, we get theta is equal to cos inverse of 19 by 21. Shortest distance between two lines. If two lines in space intersect at a point, then the shortest distance between them is 0. Also, if two lines in space are parallel, then the shortest distance between them will be the perpendicular distance, that is, the length of the perpendicular drawn from a point on one line onto the other line. Further, in a space, there are lines which are neither intersecting nor parallel. In fact, such pair of lines are non-coplanar and are called skew lines. For example, let us consider a room of size 1, 3, 2 units along x, y and z axis respectively.
Shortest distance between two lines. The line GE that goes diagonally across the ceiling and the line DB passes through one line corner of the ceiling directly above A and goes diagonally down the wall. These lines are skew because they are not parallel and also never meet. By the shortest distance between two lines, we mean the join of a point in one line with one point on the other line so that the length of the segment so obtained is the smallest. For skew lines, the line of the shortest distance will be perpendicular to both the lines.
Distance between two skew lines. Let L1 and L2 be two skew lines with equation R vector is equal to A1 vector plus lambda B1 vector, equation 1, and R vector is equal to A2 vector plus mu B2 vector, equation 2. We now determine the shortest distance between two skew lines in the following way.
Shortest distance between two lines. Cartesian form. The shortest distance between the lines L1, x minus x1 by A1 equal to y minus y1 by B1 equal to z minus z1 by C1 and L2, x minus x2 by A2 equal to y minus y2 by B2 equal to z minus z2 by C2 is mod x2 minus x1, y2 minus y1, z2 minus z1, a1, b1, c1, a2, b2, c2 by root b1, c2 minus b2, c1 whole square plus c1, a2 minus c2, a1 whole square plus a1, b2 minus a2, b1 whole square. Distance between parallel lines. Take any point S on L1 with position vector A1 vector and T on L2 vector with position vector A2. Then, the magnitude of the shortest distance vector will be equal to that of the projection of ST along the direction of the line of the shortest distance. If PQ vector is the shortest distance vector between L1 vector and L2 vector, then it being perpendicular to both B1 vector and B2 vector, the unit vector n cap along PQ vector would therefore be n cap equal to B1 vector into B2 vector by mod B1 into B2. Equation 3. Then PQ equal to dn, where d is the magnitude of the shortest distance vector. Let theta be the angle between ST vector and PQ vector. Then PQ vector equal to ST vector mod cos theta. But cot theta equal to mod PQ vector into ST vector by mod PQ vector into ST vector. Mod d n cap into A2 vector minus A1 vector by dSt, since ST vector equal to A2 vector minus A1 vector. R equal to A1 vector plus mu b2 vector equal to mod b1 vector into b2 vector into a2 vector minus a1 vector by st mod v1 vector into b2 vector from 3. Hence, the required shortest distance is d equal to pq equal to mod st cos theta, or d equal to b1 vector into b2 vector into a2 vector into a1 vector by mod b1 vector into b2 vector.
Distance between parallel lines. If two lines L1 and L2 are parallel, then they are coplanar. Let the lines be given by r vector is equal to a1 vector plus lambda b vector, equation 1, and r vector is equal to a2 vector plus mu b vector, equation 2, where a1 is the position vector of a point S on L1 and a2 is the position vector of a point T on L2. As L1, L2 are coplanar, if the foot of the perpendicular from T on the line L1 is P, then the distance between the lines L1 and L2 is equal to modulus of TP. Let theta be the angle between the vectors st vector and b vector. Then b vector cross st vector is equal to modulus of b vector into modulus of st vector into sine theta the whole into n cap, where n cap is the unit vector perpendicular to the plane of the lines L1 and L2. But st vector is equal to a2 vector minus a1 vector. Therefore, from 3, we get b vector cross a2 vector minus a1 vector is equal to modulus of b vector into pt into n cap, since pt is equal to st sin theta. That is, modulus of b vector cross a2 vector minus a1 vector is equal to modulus of b vector into pt dot 1, as n cap is equal to 1. Hence, the distance between the given parallel lines is d is equal to modulus of pt vector is equal to modulus of b vector cross a2 vector minus a1 vector by modulus of b vector. Find the shortest distance between the lines L1 and L2 whose vector equations are r vector is equal to I cap plus j cap plus lambda into 2I cap minus j cap plus k cap, equation 1, and r vector is equal to 2I cap plus j cap minus k cap plus mu into 3I cap minus 5j cap plus 2k cap, equation 2. Solution. Comparing 1 and 2 with r vector is equal to a1 vector plus lambda b1 vector and r vector is equal to a2 vector plus mu b2 vector respectively. We get a1 vector is equal to I cap plus j cap, b1 vector is equal to 2I cap minus j cap plus k cap, a2 vector is equal to 2I cap plus j cap minus k cap, and b2 vector is equal to 3I cap minus 5j cap plus 2k cap. Therefore, a2 vector minus a1 vector is equal to I cap minus k cap, and b1 vector cross b2 vector is equal to 2I cap minus j cap plus k cap into 3I cap minus 5j cap plus 2k cap. From the above, we get modulus of b1 vector cross b2 vector is equal to the root of 9 plus 1 plus 49 is equal to root 59.
Plane. A plane is determined uniquely if any one of the following is known. 1. The normal to the plane and its distance from the origin is given. That is, equation of a plane in normal form. 2. It passes through a point and is perpendicular to a given direction. 3. It passes through three given non-collinear points.
Equation of a plane in normal form. Consider a plane whose perpendicular distance from the origin is d. D is not equal to 0. If ON vector is the normal from the origin to the plane and n cap, let P be any point on the plane. Therefore, NP vector is perpendicular to ON vector. Therefore, NP vector into ON vector equal to 0. Equation 1. Let R vector be the position vector of the point P, then NP vector equal to R vector minus D n cap as ON vector plus NP vector equal to OP vector. Therefore, 1 becomes R vector minus D n cap into D n cap equal to 0, or R vector minus D n cap into n cap equal to 0, D is not equal to 0, or R vector into n cap minus D n cap into n cap equal to 0. That is, R vector into n cap equal to D as n cap into n cap equal to 1, equation 2. This is the vector form of the equation of the plane. Equation of a plane in normal form. Equation 2 gives the vector equation of a plane where n cap is the unit vector normal to the plane. Let P, X, Y, Z be any point on the plane. Then OP vector equal to R vector equal to Xi cap plus Yj cap plus Zk cap. Let L, M, N be the direction cosines of n cap. Then n cap equal to L, I cap plus M, J cap plus Nk cap. Therefore, 2 gives Xi cap plus Yj cap plus Zk cap into Li cap plus Mj cap plus Nk cap equal to D. That is, Lx plus My plus Nz equal to D. This is the Cartesian equation of the plane in the normal form. Find the vector equation of the plane which is at a distance of 6 by root 29 from the origin and its normal vector from the origin is 2i cap minus 3j cap plus 4k. Also, find its Cartesian form. Solution. Let n vector equal to 2i cap minus 3j cap plus 4k cap. Then, n cap equal to n vector by mod n vector equal to 2i cap minus 3j cap plus 4k cap by root 4 plus 9 plus 16 equal to 2i cap minus 3j cap plus 4k cap by root 29. Hence, the required equation of the plane is r vector into 2 by root 29 I cap plus minus 3 by root 29 j cap plus 4 by root 29 k cap equal to 6 by root 29. Find the distance of a plane 2x minus 3y plus 4z minus 6 equal to 0 from the origin. Solution. Since the direction ratios of the normal to the plane are 2, minus 3, 4. The direction cosines of it are 2 by root 2 square plus minus 3 whole square minus 4 square minus 3 by root 2 square plus minus 3 whole square plus 4 square, 4 by root 2 square plus minus 3 whole square plus 4 square. That is 2 by root 29 minus 3 by root 29, 4 by root 29. Hence, dividing the equation 2x minus 3y plus 4z minus 6 equal to 0. That is 2x minus 3y plus 4z equal to 6 throughout by root 29, we get 2 by root 29x plus minus 3 by root 29y plus 4 by root 29z equal to 6 by root 29. This is of the form Lx plus My plus Nz equal to D, where D is the distance of the plane from the origin. So, the distance of the plane from the origin is 6 by root 29. Find the coordinates of the foot of a perpendicular drawn from the origin to the plane 2x minus 3y plus 4z minus 6 equal to 0. Solution. Let the coordinates of the foot of the perpendicular P from the origin to the plane is x1, y1, z1. Then, the direction ratios of the line OP are x1, y1, z1. Writing the equation of the plane in the normal form, we have 2 by root 29x minus 3 by root 29y plus 4 by root 29z equal to 6 by root 29, where 2 by root 29 minus 3 by root 29, 4 by root 29 are the direction cosines of the OP. Since direction cosine and direction ratios of a line are proportional, we have x1 by 2 by root 29 equal to y1 by minus 3 by root 29 equal to z1 by 4 by root 29 equal to k. That is, x1 equal to 2k by root 29, y1 equal to minus 3k by root 29, z1 equal to 4k by root 29. Substituting these in the equation of the plane, we get k equal to 6 by root 29. Hence, the foot of the perpendicular is 12 by 29 minus 18 by 29, 24 by 29.
Find the vector and the Cartesian equations of the plane which passes through the point 5, 2, minus 4 and perpendicular to the line with direction ratios 2, 3, minus 1. Solution. We have the position vector of point 5, 2, minus 4 as A vector is equal to 5i cap plus 2j cap minus 4k cap and the normal vector n perpendicular to the plane as n vector is equal to 2i cap plus 3j cap minus k cap. Therefore, the vector equation of the plane is given by r vector minus a vector dot n vector is equal to 0 or r vector minus 5i cap plus 2j cap minus 4k cap dot 2i cap plus 3j cap minus k cap is equal to 0. Equation 1. Transforming equation 1 into Cartesian form, we have x minus 5 into I cap plus y minus 2 into j cap plus z plus 4 into k cap dot 2i cap plus 3j cap minus k cap is equal to 0 or 2 into x minus 5 plus 3 into y minus 2 minus 1 into z plus 4 is equal to 0. That is 2x plus 3y minus z is equal to 20.
Equation of a plane passing through three non-collinear points. Let R, S and T be three non-collinear points on the plane with position vectors A vector, B vector and C vector respectively. The vectors RS vector and RT vector are in the given plane. Therefore, the vector RS vector into RT vector is perpendicular to the plane containing points R, S and T. Let R be the position vector of any point P in the plane. Therefore, the equation of the plane passing through R and perpendicular to the vector RS vector into RT vector is R vector minus A vector into RS vector into RT vector equal to 0 or R vector minus A vector into B vector minus A vector into C vector minus A vector equal to 0, equation 1. This is the equation of the plane in vector form passing through three non-collinear points. Cartesian form. Let x1, y1, z1, x2, y2, z2 and x3, y3, z3 be the coordinates of the point R, S and T respectively. Let x, y, z be the coordinates of any point P on the plane with the position vector R vector. Then rp vector equal to x minus x1 I cap plus y minus y1 j cap plus z minus z1 k cap. rs vector equal to x2 minus x1 I cap plus y2 minus y1 j cap plus z2 minus z1 k cap. rt vector equal to x3 minus x1 I cap plus y3 minus y1 j cap plus z3 minus z1 k cap. Substituting these values in equation 1 of the vector form and expressing it in the form of a determinant, we have x minus x1, y minus y1, z minus z1, x2 minus x1, y2 minus y1, z2 minus z1, x3 minus x1, y3 minus y1, z3 minus z1 equal to 0, which is the equation of the plane in Cartesian form passing through three non-collinear points x1, y1, z1, x2, y2, z2 and x3, y3, z3.
Find the vector equations of the plane passing through the points r 2, 5, minus 3, s, minus 2, minus 3, 5 and t, 5, 3, minus 3. Solution. Let A vector is equal to 2 I cap plus 5 j cap minus 3 k cap. B vector is equal to minus 2 I cap minus 3 j cap plus 5 k cap and C vector is equal to 5 I cap plus 3 j cap minus 3 k cap. Then the vector equation of the plane passing through A vector, B vector and C vector is given by r vector minus A vector dot rs vector cross rt vector is equal to 0 or r vector minus A vector dot B vector minus A vector cross C vector minus A vector is equal to 0. That is r vector minus 2 I cap plus 5 j cap minus 3 k cap dot minus 4 I cap minus 8 j cap plus 8 k cap cross 3 I cap minus 2 j cap is equal to 0.
Intercept form of the equation of a plane. In this unit, we shall deduce the equation of a plane in terms of the intercepts made by the plane on the coordinate axis. Let the equation of the plane be as given below.
Example, find the equation of the plane with intercepts 2, 3 and 4 on the x, y and z axis respectively. Solution, let the equation of the plane be x by a plus y by b plus z by c equal to 1, equation 1. Here, a equal to 2, b equal to 3 and c equal to 4. Substituting the values of a, b and c in equation 1, we get the required equation of the plane as x by 2 plus y by 3 plus z by 4 equal to 1 or 6x plus 4y plus 3z equal to 12.
Coplanarity of two lines. Let the given lines be as follows. The line 1 passes through the point, say A, with position vector A1 and is parallel to vector B1. The line 2 passes through the point, say B, with position vector A2 and is parallel to vector B2. Thus, vector AB is equal to vector A2 minus vector A1. The given lines are coplanar if and only if vector AB is perpendicular to vector B1 into vector B2. That is, vector AB into vector B1 into vector B2 is equal to 0, or vector A2 minus vector A1 into vector B1 into vector B2 is equal to 0.
Cartesian form. Let x1, y1, z1 and x2, y2, z2 be the coordinates of the point A and B respectively. Let A1, B1, C1 and A2, B2, C2 be the direction relations of B1 vector and B2 vector respectively. Then AB vector equal to x2 minus x1 I cap plus y2 minus y1 j cap plus z2 minus z1 k cap. B1 vector equal to A1 I cap plus B1 j cap plus C1 k cap and B2 vector equal to A2 I cap plus B2 j cap plus C2 k cap. The given lines are coplanar if and only if AB vector into B1 vector into B2 vector equal to 0. In the Cartesian form, it can be expressed as x2 minus x1, y2 minus y1, z2 minus z1, a1, b2, c1, a2, b2, c2 equal to 0. Equation 4. Show that the lines x plus 3 by minus 3 equal to y minus 1 by 1 equal to z minus 5 by 5 and x plus 1 by minus 1 equal to y minus 2 by 2 equal to z minus 5 by 5 are coplanar. Solution. Here x1 equal to minus 3, y1 equal to 1, z1 equal to 5, a1 equal to minus 3, b1 equal to 1, c1 equal to 5. x2 equal to minus 1, y2 equal to 2, z2 equal to 5, a2 equal to minus 1, b2 equal to 2, c2 equal to 5. Now, consider the determinant mod x2 minus x1 y2 minus y1 z2 minus z1 a1 b1 c1 a2 b2 c2 equal to mod 2 1 0 minus 3 1 5 minus 1 2 5 equal to 0.